All right. So the order is not that we do this isn't super important, but again, I think I've said this in the past. Just picking a standard order that you're comfortable with, and I mean, why not do it the way your teacher does it, I guess, but if you want to do it a different way, that's fine. Maybe you want to do the derivatives first, I don't know. And then do all the points at the end when you've got all the information, and if you want to use your calculator, that might be a good way to do it, I don't know. So it's up to you, but pick one so that's not something else you have to think about. Do enough of these so that you have some habits associated with it. It just makes the whole process easier, quicker, a little less taxing on you. You can think about the hard parts and the easy parts. You kind of just do it. Okay, so we are going to start with the intercepts. And we're not going to draw out a sketch of e to the x or ln x, those graphs this time, but we do want to think, but we have them from yesterday so you can refer back to them. And again, there is some holistic kind of just, we got to think about what's happening here. Just sort of do some problem solving, do some thinking, and at various stages. Sometimes we want to think about, well, what are the asymptotes involved in the sort of basic functions that are involved in the sketch? What are how does it grow? When we look more carefully at our asymptotes, we have to look at how it grows and kind of examine that. For this one, and think about where intercepts occur. So where do y-intercepts occur? Well, when x is 0, if I put 0 in, I get 3 times 0 on top, e to the 0, which is 1, but I get 0 on the bottom. So there is not going to be a y-intercept. And in fact, you could write it down now, but I think we're noticing that there's likely an asymptote there. I say likely because it's not actually for sure that there's an asymptote necessarily, but there's likely one. Okay? Because the function does, what we can say, the function does not exist when x equals 0. So there's no y-intercept. What about an x-intercept? An x-intercept occurs when you set y equal to 0, and when y is 0, the numerator is going to be 0. That's when we're interested in. So e to the 3x equals 0. And what do you think about that? This is where we can use our understanding of that graph. What does that graph look like? Does it ever touch 0? I guess you could rewrite it as a logarithm, but probably the easiest way to think about it is the graph. And so this never happens. No x-intercepts either. So no intercepts of any kind. Interesting. Again, in these kinds of graphs, anything's possible. All right, let's start looking at asymptotes. We'll do vertical asymptotes first. So maybe there's one at x equals 0. So how do we test a vertical? Again, these are all the questions. Like, don't just let me do the thinking. You right now can think to yourself, how do I do the testing around a vertical asymptote? And I said this yesterday, and I mean it. Especially if you have a calculator that you can use with the memory functionality that we've talked about, it's pretty easy to test a couple of values. Do it. It's worthwhile to test a couple of values because with exponential growth, it happens so fast that weird things can happen. You can get very close to, like quite close to an asymptote and be misled about what's happening. So it's nice to look for a trend. In fact, if I don't know if you had a different teacher for MHF, I'm not sure, but if you had me, we talked a little bit about this, about the idea of like getting progressively closer and seeing how it changes. And you can kind of, in the numbers, you can see what's happening with the asymptote. It's an interesting thing. So I would recommend doing that. Let's see, e to the 3a divided by a. That's what it looks like to use the memory on my calculator. Hit equals. Let me finish this. So I'm going to pick something very close to 0, but negative because it's to the left. So negative 0.1. And let's see what happens. Store that in A. I get negative 7. Negative 0.01. Store that in A. Whoops. Store that in A. I get negative 97. So that was like a lot of growth. So that looks to me like, sure enough, negative 0.001. Just do one more. Store it into A. And I get negative almost 1,000. So like, yeah, you can see the trend when you've done a few. It's going to negative infinity. And then the limit as x approaches 0 from the right of y. We do the same thing, punch a few values in, and I think we find that this one's going to positive infinity. It is possible that you are doing that test and it's not trending to negative infinity or positive infinity, it's trending towards some number. Okay, that can happen. So again, you can't take for granted by punching in one value or by guessing or something like that. You do have to test these things. And the 4 graphs in the homework, the 2 yesterday and the 2 from today, are all quite different. And the one we're looking at here is different again. So like you want to have done all 4 of them for sure. Better than just looking at the solutions online is to do them yourself, of course, and get a sense of the different kinds of things that can happen. Okay, horizontal asymptote, oblique asymptote. What does this test look like? How do we do this one? Remember we talked about this yesterday. For the horizontal or oblique asymptotes, it's not about what's happening in the middle of the graph. That could be going up and down. There could be vertical asymptotes occurring. It's about what happens at the extreme 2 ends. So we do this. As x goes to negative infinity, we ask, what does y do? And we just look at the function. And what do you think is happening? So you might think e to the 3x, I'm looking at, I'm visualizing the graph. So the negative infinity is going way off to the negatives. What happens to e to the x? It gets small, 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 small. So I get something really small trending to 0 on top. So like 0 on top. And then the bottom is just x. So the bottom is negative infinity. Negative infinity, positive infinity, same thing. A big number in the denominator makes for a small number overall. So what's happening? What would be your guess? It's approaching 0. So we have a horizontal asymptote. And then, I might want to leave a little bit more space here. What happens is x goes to positive infinity. And this is where you got to look at this balance. So I've got e to the 3 infinity on top. That's going to get really big really fast. And I've got x on bottom, which is going to get big like this one. But which one's going to take over? So here's the tricky thing. If it was like 2x over x, it's like, oh, 2's bigger. No, 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 no. The fact that it has a multiplier doesn't really make that much of a difference when we're talking infinities. Does that make sense? So 2x over x wouldn't be like, oh, you got 2 infinities on top and 1 on the bottom, so the top's winning. That would be like they would kind of equal each other out. But exponential growth, is huge. So that's going to win. So on this side, we've got y going to infinity, so we don't have any asymptote. I'm going to let, f at x equal y, and I'm going to check f at, let's check, so we're going off to the left, so we're going to check negative values. I remember we talked yesterday about negative 10. I've still got my function in my calculator, so this is easy to do. Negative 10, store it in A, go up, and I get something funky. Is anybody else doing this, or are you just letting me do it? It's okay if you are. It would take you a few minutes, but I get like negative something strange. It's actually like 9.3576 times 10 to the negative 15. So if you know a little bit about scientific notation, that's a very small number. I could put in a more negative one. I'm not going to get too much more negative, though. I'm going to go, let's say, negative 12. And now I get 10 to the negative 17. So the exponent's getting even smaller. So, like, this is working. But I don't like those numbers, so I'm going to actually backtrack it. I'm going to try negative 5 and see what I get. And here we go. I get something that's just a little bit easier to think about. It's really, really small, negative 0.000000. I think I got that right. There might be one more 0. 6. Very, very small. And that's just below 0. So, and it's getting smaller as we go out further very, very quickly. See what I mean by like putting in, what would happen if we put in negative 100? That was our old test. My calculator's going to like explode or something. Yeah, give me 0. Actually, it said 0. My calculator can't even, like, it just doesn't have enough digits. It would go off the chart so far that it just says 0. Okay, so a little messy. It's a little messy, and that's all there is to it, unfortunately. Okay, I think we've got all of this done. So we've got our intercepts, we've got our asymptotes. I am now going to do both the first derivative and the second derivative. I'll let you get a head start if you want to give it a try yourself. Quotient rule. So the derivative of the top is e to the 3x times the derivative in the exponent, which is 3. So that's the derivative of the first part, and then times the bottom, which is x. I could see somebody getting confused about thinking that x came from the exponent or something like that, or like forgetting, like if you're just trying to read this and not following along, it'd be like, where did that x come from? Minus the top times the derivative of the bottom, which is just 1 over the bottom squared. I'm going to factor this. I would be curious for somebody, I should just do this myself, but when we do the second derivative, which one do we want to use? Because either way, we're going to get a bit of a disaster where we're getting product rule and quotient rule in the same question. It's quotient rule because I've got a quotient, and when I take the derivative of the top, I've got a product. Here's the product here, e to the 3x times 3x. So that part's going to be easy, but this part's going to be product rule. Or it's this times this, product rule. I think it's going to work out almost identically no matter which way you do it. I'm going to use the second line. So derivative of the top, which is product rule. So then I go into product rule, which is the derivative of the first thing, e to the 3x times 3, times the second thing, 3x minus 1, plus the first thing, times the derivative of the second thing, which is that whole polynomial expression, which is just 3. Look carefully, though, because that was the derivative of the first, that was the derivative of the top, and that's times the bottom for quotient rule. So I got to put brackets around that whole thing and times x squared. And then minus the top, e to the 3x. I don't know if I really need those square brackets actually, but minus 1 times the derivative of the bottom, which is 2x. All over the bottom squared, so x to the 4. Any questions? I don't think you need to write every one of the next steps down. So maybe you just want to watch, because I'm going to do this kind of quickly. Stop me if you have any questions. So one thing I notice is there's an e to the 3x in every part of this. So like there's an e to the 3x here. Like if I expanded this, it'd be this times this and this times this. So I'd have two terms there. And then that whole thing is a term. So this has e to the 3x, e to the 3x, e to the 3x in it. So I'm going to take an e to the 3x out. Maybe there's something else in there, but I don't think so. Okay, so I'm going to take that whole thing out. And then when I'm looking at this part here, that was the first thing I took this out, so I only have that left, so I'm going to expand it. So 3 times 3x minus 1 is 9x minus 3 plus 3, because this e to the 3x is gone, times 3, so that's just that. All of that times x squared. Minus, I took the e to the 3x out, so I can expand the rest of this. I've got 3x minus 1 times 2x, and I'm subtracting all of that. So this is minus, I think, 6x, and then plus 6x squared plus 2x. Does that look right? I think we're good. Over x to the 4th, which equals e to the 3x. We're going to solve this anyway, so I never want to expand that back through. I want to leave that out, right? 9x minus 3 plus 3 is obviously 9x. 9x times x squared is, and I think I have, sorry, I should have, I'm going to do this. I'm going to go back and fix this. That should be like that because I factored the e to the 3x out of the whole thing. That looks better. Okay, so now I have 9x cubed minus 6x squared plus 2x. And then what I can do is get rid of one, factor out one of those x's and divide it with what I have on the bottom. And this is, you can write this is our last step, 9x squared minus 6x plus 2 over x cubed. Nasty. Any questions? We okay with that? You're thinking to yourself, well, I more or less followed what you did, but could I do that? I mean, you could, just got to do it carefully, right? You just got to take your time. It's not that bad. All right, let's look at critical values. So when y prime does not exist or equals 0. Y prime does not exist when x is 0, but that's an asymptote. So we're good there. So what about when y prime equals 0? That's when e to the 3x, nope, sorry, I'm looking at the wrong one there. That's when e to the 3x times 3x minus 1 equals 0. e to the 3x will never equal 0. We've already talked about that. So therefore, x equals 1/3. It's just that other bracket. That's the only one we have. What about points of inflection? So here, I'm going to come down here, and I'm going to look at this expression. Does not exist when x equals 0, but again, that's a vertical asymptote, so we're good. This part is never 0, as we've talked about every time. And this last part, b squared minus 4ac, turns out to be less than 0. I believe it's negative. Therefore, no solutions here either. So what did we just discover? No POIs. It's unusual. Don't you think? So what do we do next? Very nice. We still can do our second derivative chart with the vertical asymptote because concavity can switch over at an asymptote. That would still be included even if we had other POIs. We'd still need to include asymptotes as well. I love it. So x, and that's at 0. So when x is less than 0, at 0, and when x is greater than 0. And we look at y double prime and y. So again, I wouldn't pick giant values less than 0. Pick -1, -2, -3, so you get reasonable things. We get a negative here, so that's concave down. This does not exist. It's a vertical asymptote. And then we get positive here, so it's concave up. And what's the last thing that we have to think about? The critical value, which occurs at 1/3. So where is that? That's here. It's concave up. So it's going to look like this. So if I have a critical value there, what is it? It's a local minimum. At 1/3. And I think I still have the original function in my calculator here. So I'm just going to punch this in. 1/3. And I get approximately 8.15. But when I look up at the function, what do I get here? When I put 1/3 in here, that's just gone, so that's just e. Like e, right? It's 3 times 1/3, so that's 1. So this top is just e. E over 1/3 is 3e. So sometimes it's not a bad idea, especially if it's just in your homework, that kind of thing, to challenge yourself to just check and see if it's easy to evaluate exactly. But in the end, the 8.15, I think if you do 3e on your calculator, you can find them to be the same. The 8.15 is kind of the one that we want because that gives us a sense of where it is anyway. But all right, I think we're good. Ready to sketch this guy out. I have a vertical asymptote at x equals 0. I have a horizontal asymptote going out this way at y equals 0, but not going the other way. You can draw it all the way along. I don't care about that, but we don't need it going off to the right. Let me go back up and review my asymptotes. As it approaches from the left, the vertical asymptote, it's going down to negative infinity. As it's approaching from the right, it's going to positive infinity. So going back up, it's going to look something like this and something like this. As it approaches my horizontal asymptote, going to the left, as x goes to negative infinity, in other words, it's approaching 0 from below. So look what's happening here. Whoa. If I can zoom in on this properly, it's going to be something like this. No POIs, no maxes or mins. There's no little blips or anything in there. It just looks like a good old rational function, reciprocal function. Something like that. And what happens here, as x goes to positive infinity, y goes to positive infinity, so it's just going off out into that quadrant somewhere. It's got a local minimum, and it comes down here. So just does that. And this point is my point A here. Critical value. That's it. Any questions?